왔다. 잠깐만, 뭐가 문제지? 응? 혹시 도훈이 있어? 도훈 좀 바꿔줄래? 도훈아 혹시 유튜브 볼 수 있니? 나오니? 어, 내 거 실시간에서 뭐 오류가 발생했다고 나오는데. 그래? 얼굴 보여? 근데 내 화면만 그런가? 잠깐만, 그럼 이거 어떻게 봐야 되나? 그래, 알겠어. 음, okay, hello everybody. Okay. Okay, hello everybody. Speaker is a problem. Okay. Let me turn off. Hold on a second. Actually, my YouTube channel is a little bit weird today. Sorry about it. Actually, I lost the main screen where I broadcast my lecture. I lost the main screen. So that's why I'd like turn it off. And then, well, because I lost the connection, that's why today for me it is very difficult to get your questions. Okay, so let me start my lecture. So if you don't have if you have some problems, please please notice my TA for the problem so that I can repeat. I have a little problem today. Let me talk with my TA. Oh, wait a minute. Maybe I can turn my speaker off. Yeah. So that I can see the chatting window. Alright, now I can see all the chatting windows. So I turn off my speaker to prevent any echo problem. Alright, so let's go for today's lecture. Alright, so we are working for one-dimensional problem, right? So if you, now because I can see the chatting window, if you have questions, please let me know by typing your questions in this chatting window. Alright, last time, after the last time, after the last lecture, so I have a question from a student that it seems that he doesn't understand clearly the concept of the analysis for the statically indeterminate structures. So that's why I'd like to revisit the problem again. Alright, so what kind of problems that we want to use? For example, let's consider a simple problem to help you understanding. So how about this problem? So let's consider this problem. Okay, so to simplify the problem, so I want to consider a horizontal view of the same problem. Okay, say I have a bar. I have two bars. And then as given in the note, so I'd like to note here is A and B. And then at point C we have a concentrated load conceptually. And then its magnitude is given by P. And then here the elastic modulus of the first part is given by E1. And then the cross-sectional area is also given by A1. And then let's say this guy is E2, and then its area is A2. And then we need the length of each segment, isn't it right? So here we'd like to call this length is L1, and then this is L2. Okay, this is the problem. Okay, obviously this is statically indeterminate structures because we can imagine that there is a reaction, so RA and then RB. So I told you, as I emphasized you several times, that before any analysis, what I mean any mechanical analysis. So whenever we use any mechanical analysis, the very first step that we have to take is to define a proper coordinate system. Otherwise, we cannot continue our analysis, isn't it? Because we want to use, some kind of mathematics to deal with all the vectors. Here we have force vectors and the reaction vectors, and also we need to consider the internal forces, and then with respect to different choices of free body diagram, and then also we have to check the force equilibrium conditions using the vector concepts. What I mean, according to the force equilibrium condition, isn't it right? So the very first step, whatever we do, as long as you want to do analysis. So we have defined a coordinate system. Let's say this is my default coordinate system. This is my default x direction. We'd like to choose the right hand direction is default positive direction. Is it clear? So now let's check the physical meaning of the statically indeterminate structures. So force equilibrium for forces. Here we would like to emphasize the external forces and reaction forces. So please make sure that what are structures actually. Here, this is my structures, okay? So with respect to these structures, we have three different kinds of external forces. The first one is what? The first force is the external force P, and then we have two unknown external forces, the reactions, okay? So we have three external forces. But conventionally, the unknown external forces are called reaction forces. But make sure that basically, these are kind of the external forces, because the blue part is my structure. Is it clear? Okay, so let's check the force equilibrium. So if you check the force equilibrium, the sum of all the forces in that direction should be equal to 0. Okay, so basically we have to use the force equilibrium for force vectors. So we have to use the force equilibrium condition for force vectors. But fortunately, so we introduce a coordinate system. Because we have a coordinate system, so instead of dealing with the vector itself, so we can handle the vector components only. Okay, now we can consider the vector components only. Okay, for the given coordinate. Is it clear? So because we have this coordinate system, that's why instead of checking the vectors themselves, so we can check the force components. Okay, that's a very important thing. Okay, so let's count all the vector components. Then first I have RA, isn't it? Because we assume its direction is the positive direction in this assumed or our coordinate system. And then RB, and then plus P is equal to 0. So according to this equation, let's say this is equation 1. According to equation 1, RA plus RB is equal to minus P. So usually the apparent external force P is given by a number, isn't it? So as long as the RA plus RB is equal to minus P, then any set of RA and RB would satisfy the force equilibrium condition. For instance, so let's consider P is equal to, say, 10 kilonewton. And then we want to choose, for example, RA is equal to, say, 1 kilonewton. And then RB is equal to minus 11 kilonewton. Look at this. So 1 minus 11 is equal to minus 10. And that satisfies the force equilibrium condition perfectly. Okay. And then how about this? This is one choice. Or we can consider the RA is equal to minus 5 kilonewton. And then RB is also minus 5 kilonewton. That also satisfies the force equilibrium condition. However, for example, another example, so RA is equal to RA is equal to minus, what's wrong? Minus minus 5 kilonewton, and the RD is, say, for example, 4 kilonewton. So in that case, this guy doesn't satisfy the force equilibrium conditions given in equation 1. Okay, it doesn't. So this guy, yes. This guy also, yes. Okay. Why this problem happens? Because we have only one equation for two unknowns. That's why we have infinitely many sets of reactions which satisfy force equilibrium condition. Unknown force equilibrium condition. Yes. Okay. That's the problem. So in the case of such kind of statically indeterminate structural systems, so we cannot determine the reaction forces using the force equilibrium condition alone. What I mean, between the external and the reaction forces. Is it clear? That's the key point to understand the characteristics of statically indeterminate structures. Isn't it right? So we have two unknowns, but we have only one force equilibrium condition. That's why we cannot determine all the reaction forces specifically. That's the problem. Alright, and then let's try to solve this problem. Okay, first, I want to simplify the problem in this way. Say, because the drawing is too detailed, instead of using this, I want to consider the simplified diagram. So what's wrong? So okay, simply let's use new page. Say, and then here I have RA, and then obviously it's a support here, and then also I have a support, and then reaction RB, and then I have P here, P, and then its length L1, oh, sorry, capital 1, capital L, L1 and L2, and then the material properties, sorry, and then cross-section areas are given in this way. Okay, so let's consider this problem. So I wonder if you remember the principle of superposition. Principle of superposition. In 우리말 it is called 중첩의 원리. Okay, so since we are using linear elasticity, as long as we use linear system, so we can superpose the response. Okay, that's the 중첩의 원리. Okay, let's consider this 중첩의 원리. Alright, so this system is equal to, I have a structure system. Okay, I have a structural system. I can imagine two different kinds of structural system. Let's say this is, I want to call this is system 1, and then this is system 2. Here we'd like to apply only P, and then here I want to apply 1, and then I'd like to multiply the overall response by RB. That's what I want to do. By the way, maybe better to use this multiplication outside of this box conceptually. So RB. Okay? And then because here maybe I have RA, reaction RA in system 1. Okay? And then again, here we may calculate the reaction RA, but for system 2. So according to the 중첩의 원리, or principle of superposition, the real response, not real, so wrong choice of terminology. So actual response, sorry about it. So actual response, or the behavior of my system, is equal to response of system 1, okay, plus response of system 2, and then multiplied by the unknown RB. Okay, this is the principle of superposition for linear system. So what I'm going to do is this. Obviously here we have one unknown. So RB is unknown, isn't it? And then for system 1, so if you consider suitable boundary condition, so let's say this is my boundary condition. So in the original problem, our problem was because I have two different boundaries and two different reactions, and I have a one-in-one force equilibrium condition in that direction. That's why we were not able to determine all the reactions, except we can find, there are infinitely many sets of equilibrium sets, or reaction sets, which satisfy the force equilibrium condition. So instead of having these two different places of the boundary conditions, so here we want to consider only one boundary condition. Now we have only one reaction. Okay, so if you have only one reaction, then we can solve the reaction by using the force equilibrium condition. And then if you use the formula regarding the elongation of structural members, then we can calculate the displacement here, isn't it, right? And also even in system 2, so we can determine the reaction very easily, and then also I can calculate the displacement at this point. So which means, okay, instead of this actual response, I want to call this is, say, displacement at C, at B. The actual displacement at point B is equal to displacement at B in system 1, and then displacement in system 2. Here we use the unit load as the external load. Here I want to multiply with RB, because as a boundary condition, so we already know that UB is equal to 0, because this is a boundary, displacement boundary. So what does it mean then? Then we can, using this, UB is equal to 0. That means my reaction RB can be calculated as RB is minus UB in system 1 and then UB in system 2. That's how we can determine the reaction. So once I determine the reaction, using the reaction value, I can calculate the internal stress in different part of the structures, for example section 1 and section 2. That's how we can finish our analysis. Alright, so let's consider system 1. I don't know what's wrong today. It's not working smoothly. So let's consider system 1. As I told you, in the case of system 1, we have force. Sorry. Sorry about it. I don't know what's wrong. So let's use new page. Okay, so let's consider system 1. In the case of system 1, so we have force P here, and then so I want to consider displacement boundary condition, point A, and then I have unknown reaction RA here. Alright, so let's try to calculate the elongation. So how do you calculate this elongation? So we already know the formula. The elongation is equal to L1 over E1 and A1, and then I have internal force P. This is my elongation. Or if you want to 1 by 1, yes, let's consider 1 by 1. So instead of using this formula directly, first let's try to calculate the reaction. So if you want to calculate reaction, we have to introduce the coordinate system. The sum of all the forces in this direction should be equal to 0 if we want to use the force component only. So RA plus P is equal to 0. This is the force equilibrium condition. Then we can determine the reaction very easily. So RA is equal to minus P. Okay? So now let's determine the internal force. So I want to build a free body diagram. So let's consider the free body diagram here. Okay. So if you consider this free body diagram, then okay, here, because there is no, well, let me extend the free body diagram like this, because this part there's no force. This better. So this is my free body diagram, and then I can imagine I have an internal force N, and then I have external force P. So please make sure that this guy is external force, and then this guy is internal force. So I told you several times that internal force is what? The stress resultant. So which means the sign convention or the characteristics of internal, anything internal, so must inherit the characteristics of the stress. Okay, so which means the sign of internal force is positive if the internal force stretches the material. So look at this. So I have the material, and then this internal force stretches this material. That's why this is default positive. So now I want to check the force equilibrium for this part. So let's consider the force equilibrium for this free body. The sum of force in this direction is equal to 0. And then here, so although the internal force itself is positive, but for checking the force equilibrium, because this is the default positive direction for the force, and then this is minus N plus P is equal to 0. That's why we can conclude that my internal force is equal to P. Is it clear, right? Okay. So once I have internal force, look, so always refer to this diagram, this diagram. So I have force, and then displacement, and then stress and strain. This is my diagram, right? So this is the flow of analysis from the displacement and the strain, stress, and the force. And then from force, stress, strain, and then displacement. So always one condition in one step. So do not consider more than one condition. It's confusing, and then you don't have to do that. Okay. So actually, in the case of smart students, they can consider the multiple conditions at the same time, but not necessary. You don't have to do that. Okay, it's the easiest 1 to 3. And then, as I told you several times, so I emphasize you many times. And this is what? This is structural level information, and then this is material level information here, material point. And then between these two levels, we may consider another level, so member level. So if you consider member level, we may have here what the internal force N, and then the elongation delta. Okay. So if you don't want to go deep into the material point, maybe you can just stop your analysis up to the level of internal force and the elongation and then displacement. And also the same from the displacement, the elongation, and the internal force, and then the external forces. But basically, it's same. The only difference is how deep we're gonna go into. That's the only difference. So basically, we have to consider the structure scale, and then also the material point scale. Okay, that's what we have to do. But if you have a shortcut formula, like the delta, the elongation delta is equal to the length times the internal force divided by the elastic modulus and the cross-section area. Then in that case, yes, we don't have to consider stress and strain. Okay. We can accelerate our calculation. So now I have information of this internal force here. Okay, so I want to consider the elongation directly. So because I have internal force N, then according to my formula, the elongation of segment 1. Okay, this is the segment 1, right? Segment 1 is equal to what? The length of the segment 1 and the internal force that we just calculated. Here I want to denote this as equation 2, the N divided by the elastic modulus of segment 1 and then cross-section area of segment 1. Here we just calculated the internal force is equal to P. So let's plug in P here. This is the elongation of that segment, L1 and P, E1 and A1. So how do you calculate this elongation? The definition of elongation, the segment 1 is what? Because this is my coordinate system, the UC, this is point C, right? And then this is point B. UC minus UA. This is the definition, isn't it, right? UC minus UA. But because of boundary conditions, UA is equal to 0. Because of the boundary condition. That's why it is equal to UC. Okay? So UC is equal to what? L1 P and then E1 over EAI. Okay, this is UC. And then make sure that there is no force here, and that this is free end, which means UB is equal to UC, isn't it? Yeah, because there is no force. L1 P E1 and A1. This is what happened in system 1. Okay, please make sure that I want to call this is equation 3. And then the next step, I want to consider system 2. Actually, last time I was able to use longer page, but why not in today? Now it's working. It's really fun. Okay, let's consider system 2. In the case of system 2, so I have a support here. Sorry. So let's use new page. Let's use system 2. I want to consider the part 1 and part 2, and then we applied unit load 1, and then we want to consider the displacement boundary condition. Say this is point A and B and C and B. Okay, again, the structural system is exactly the same as before. Okay, so what we superpose the response only. Okay, the displacement, stress, and reactions only. So we have here RA. Okay, so let's use the force equilibrium. If you use force equilibrium, so we know that so RA plus 1 is equal to 0. That's why we can calculate that RA is equal to minus 1. So I want to call this as equation 4. Okay, and then here let's try to calculate the internal forces. So how do you calculate the internal force? So if you consider the free body diagram, for this part and also this part, it is really trivial to calculate the internal force, isn't it? Maybe I don't have to repeat the calculation because you don't understand what happened here. This is part 1, so L1 and L2, and then I can calculate N2. N2 is equal to 1, isn't it right? And also here the internal force in segment 1, N1 is also equal to 1. This is the free body diagram for this and for this choice of free body diagram. Is it clear? Do you have any questions? Then I can calculate elongation for segment 1. Delta 1 is what? L1 and N1 divided by elastic modulus and the cross-section area of that segment. But N1 is equal to 1, isn't it right? That's why it is equal to L1 and then E1 and A1. So make sure that we have unit value, okay? The unit value. And how about delta 2? Delta 2 is also same, E2, A2, L2, and then times 1, okay? The 5 and 6. Alright, then how do you define delta 1? So delta 1 is equal to UC minus UA. And the delta 2 is defined as UB minus UC, isn't it right? UC, yes. Okay. Here, because of boundary condition, so UA is equal to 0. That's why we can calculate UC. UC is delta 1. So let's plug in UC here. Then if you plug in here, and then my UB is equal to delta 2 plus UC. Then delta 1 plus delta 2. That means L1 times 1, so E1 A1 plus L2 E2 A2 times 1. Is it clear? So now I want to superpose. So displacement UB calculated in system 1 plus displacement UB calculated in system 2, and then I want to multiply that displacement scale by unknown reaction in the original system. Then the superposition of these two displacements should be equal to original displacement as the part of the problem, because this is boundary should be equal to 0. This is also a compatibility condition, displacement compatibility condition. Then I can determine the reaction very easily. So RB is equal to minus UB1 UB of system 2, isn't it? So minus, this is equal to, where is UB1? So UB1 is equal to L1P E1A1. So L1P E1A1. This is UB1. And the UB2 is here, system 2. So L1 E1A1 plus L2 E2A2. Okay? And this approach is called 변이일치법 in 우리말. Sorry, 변이일치법. It is called 변이일치법. Sorry, 변이일치법. And then this condition is called 적합 조건, compatibility condition. Compatibility condition. 오, in 우리말 적합 조건. Do you have any questions? Is it clear how to use this 변이일치법? So as given in the textbook. This is the one of the standard method used in undergraduate course. 수민이 변이일치법이 어느 식인가요? This one, this equation. And then we want to check, the condition for the displacement of original system. This is the 변이일치법. So in this approach, it is very important to understand, the superposition, the principle of superposition. Okay, so we decompose the original structural system into, sum of structural responses of more than one structural system. So in these problems, we want to consider two different kinds of substructural systems. Any other questions? So because since Sumini asked me questions, let me explain you a little bit more about the principle of superposition. So let's consider we have an elastic system. Let's consider we have an elastic system, linear elastic system. Okay, look. So let's consider a function. So y is equal to function of x. Let's say this is linear. So if it is linear in two-dimensional graph, so we can draw in this way, x and y. And if it is linear, then that's gonna be a straight line, isn't it, right? Is it clear? So let's consider proportional coefficients. So if it is a linear system, using a proportional coefficient, it becomes kx, isn't it? It's kx. And then its slope is equal to kx. Alright, so now problem is here. I want to consider x1 as the input argument. Then we're gonna have, so y is equal to k times x1. So the y value corresponding to x1 is equal to kx1, isn't it right? It is really straightforward. Okay, so let's consider x1. Then if you consider x1, then we can get the response y1. How about x2 as the input argument to this structural systems? So y2 is equal to kx2. Yeah. So if you consider x2, then we would get y2. So what if you apply x1 and x2? So if you apply x1 and x2, then my system, my response is equal to what? Y, k, x1 and x2. Then that means kx1 plus kx2. This is equal to y1 plus y2. Is it clear? Okay. And then this is called the principle of superposition. The response of the system for any quantity is equal to the sum of individual responses to the individual loading. That works only for the linear elastic system. Works for only linear system. This is very important. So for example, if you have a system like this, let's consider a nonlinear system. In that case, it is really obvious to find that the principle of superposition is not working. So the principle of superposition is working only for linear systems. That's very important. So assuming our system is linear elasticity, linear system, so we can use the principle of superposition. Please make sure about it. Any other questions? Okay, so if you don't have questions, let's consider another way to approach this kind of problem. Alright, say we are still using the same problem. Point A, B, and then C, we apply concentrated load P here. So I have RA and RB. By the way, how do you calculate the actual reaction at point A in the 변이일치법? First, we have to calculate the reaction in system 1, so RA1, okay? And then plus. And then we need to calculate the reaction in system 2, RA2. And then we need to multiply RA2 by RB value that we calculate by using the displacement compatibility condition. Then sum of these two reactions from system 1 and system 2, and that's gonna be the actual reaction at point A. Is it clear? Okay, so let's consider this problem. So here I want to use this path, say the force equilibrium, and then I don't know what's wrong today. So let's use new page. So here if anybody familiar with the iPad, please let me know for what happened. Okay, so here in this approach, I want to use my user diagram here, displacement, and then elongation, and internal force, or strain, stress. Okay, let's use this passive analysis, or we can consider this because we already have the formula. So I want to consider this. I want to consider this from this procedure. Okay. Okay, so first we have to define a coordinate system. I want to define a coordinate system. This is my coordinate system, and then we have to define a suitable or compatible displacement field. That's what we have to do. All right, this is my coordinate axis, and then this is my displacement. Okay, please make sure that point A is displacement boundary condition. At this point, my displacement should be equal to 0. And how about point B? Point B is also the displacement should be equal to 0. That corresponds to point A and point B. And then this is point C. Point C is here. And then point C here, the length is given by L1. This is a part of the problem. This is L2. Okay? And then I may have non-zero displacement at point C. This is UC. So although I haven't calculated the value of the nodal displacement at point C. And then because we are dealing with prismatic cross sections, so we have constant elastic modulus and constant cross-sectional area in each part, which means my strain is constant in section 1 and section 2. That's why my displacement change should be linear like this, isn't it? So can you calculate the elongation? Yes, we can calculate elongation. So elongation of segment 1 is equal to what? UC minus UA. And this is equal to what? UA is equal to 0 because of the boundary condition. This is equal to UC. And the elongation of segment 2 is equal to what? UB minus UC. And then again, because of boundary condition, UB is equal to 0. This is equal to minus UC. Is it clear, right? Okay. So now we are here. Now we are here. Now we are here. We just defined displacement boundary displacement distribution, and then using the displacement we calculate the elongation. We are here. Okay, we were here, and then we calculate the elongation. The next step is we need to calculate the internal force. This is very easy, easiest 1, 2, 3. Do not consider many equations at the same time. Always consider one equation in one step. Okay, then we need to calculate the internal forces corresponding this elongation. Then I need to calculate the internal force of segment 1 and 1. Okay, when you calculate the internal force for segment 1, what elongation you need? Elongation of segment 1 or elongation of segment 2? If you want to calculate the internal force of segment 1, do you need the elongation for segment 1 or segment 2? No response. So obviously because we are interested in that member only, that's why if you want to calculate the internal force for member 1, then you need elongation for member 1, not member 2. Okay, it is really obvious. So N1 is what? The internal N1 is the length 1 and the elongation 1 and the elastic modulus of 1, the cross-section area of 1. Okay, because here I have elongation of that elongation is equal to UC. This is equal to L1 UC and then E1 A1. Okay, how about the internal force of segment 2? Internal force segment 2 is again by the same logic. This is E2 A2 L2 in the elongation of segment 2. The elongation of segment 2 is given by minus of nodal displacement of point C. That was displacement comparability condition. So minus L2 UC and then what? It's E2 A2. Is it clear, right? So we just calculated the internal forces. Okay. So now we have determined the unknown. So we have one unknown. So UC. This is my UC. Okay. So let's consider a suitable choice of the free body diagram. So what part you want to consider as the free body diagram to determine the unknown? So let's use this part. Okay. So if you use that part, then I have what? I have external force P, and then I have one internal force. This is for part 1 and 1. So same again, the nature of internal force is what? It's the same as the nature of stress. That's why, you know, when you consider default positive internal force, you need to consider how stretch the material or how stretch the member. And this is N2, isn't it? So let's consider the force equilibrium. So if you consider force equilibrium, all the force component in that direction should be equal to 0. That's why minus N1 plus P plus N2 should be equal to 0. Alright, so let's plug in the information of N1 and N2 here. So N1 is minus L1 UC E1 A1 plus P and the minus L2 UC E2 A2 should be equal to 0. So you can determine the nodal displacement of point C very easily, right? So UC is equal to, so P, P. Now how can I freeze this screen? P L1 sorry about it. Let's use this space. UC is equal to P L1 E1 and A1 plus L2 E2 A2. Okay? Is it clear? So if you don't mind, here I'd like take a break. I'd like take a 10 minutes break. So it's really mystery why it is not working as usual. It's really funny. But now it's working. Why? Uh-oh. Do you have any questions? So if you have questions, please let me know. You know, there's a right attitude as a student. So please feel free about questions. You know, it doesn't matter your question, you know, how silly your question would be. It doesn't matter about it. So if you don't understand any point, you know, other students would have, you know, would be in the same situation. So your question would help other students understanding. That's why feel free about your questions, okay? So any questions are very, very welcome. 동현이 internal force는 멤버 어느 지점이나 동현이 actually usually it is not. For example, if you have how to say if you have distributed forces in members, then your internal force must change to satisfy the force equilibrium condition. But if you have nodal forces, if you have external forces at only the nodal points, then your internal force should be same. Okay, there's no change. Otherwise, we cannot satisfy the force equilibrium condition. Okay? 근데 혹시 아이패드 잘 아는 친구들 있는가? 이거 왜 지난번에는 잘 넘어가더니 오늘은 이게 안 넘어갔나? 왜 그러는지 모르겠어. 노트를 몇 장을 썼는지 모르겠고. 다른 질문 없어요? 뭐 지금 다들 잘 따라오시고 있는지 잘 모르겠네요. 현민이 일롱게이션 공식을 변형하면 내력은 일롱게이션이 나오는데 교수님이 필기해 주신 책과 왜 다른가요? 아, yeah, that's a really good point. That's my error, sorry. Oh, thanks a lot. It should be corrected. It should be okay. Sorry about it. This is stiffness L1 and delta 1. Yeah, you're right. Thanks. Is equal to E1 and A1 L1. You see. Oh, you got me today. And this is equal to E2 A2 L2 delta 2. L2. And then that should be changed to, right? So E1 A1 L1. E2 A2 L2. And then this guy should be also changed to E1 A1 L1. E2 A2 L2. Thanks. Okay, thanks for that. I asked my TA to give you a participation credit for your questions. Any other questions? So if you don't have questions, let's move to the next subject. So next subject is thermal effect. So, but here I want to, instead of using the terminology of thermal effects, I want to call, non-mechanical strain. So next subject is thermal effect. So I'd like to generalize this thermal effect to non-mechanical strain. Okay, let's look at this Hooke's law. The Hooke's law says that, what's Hooke's law? Hooke's law is stress is linearly proportional to strain, but specifically the mechanical strain. Okay? But if you look at inelastic system, the stress and strain, let's say you have this inelastic material behavior. So look at this. So if you apply for a certain value of strain, you can get the corresponding stress value. So if you have the functional form of stress-strain relation. But when you define the deformation, then we may have different sources of deformation. So let's consider deformation. So we have different reasons for certain deformation. Deformation by load, by stress, or deformation by temperature change, deformation by humidity change. There may be many other reasons for a certain kind of deformation. But stress is caused by the strain. Okay, please refer to my diagram. Force and stress and strain, and then displacement. Okay, displacement field causes strain, strain causes stress, and stress causes the internal forces to satisfying the force equilibrium condition. So when you look up the strain, we may have many different sources of strains. So total strain. So let's consider total strain. Total strain is strain caused by stress, or strain caused by temperature change, strain caused by humidity change. So as given in our textbook, let's see, the misfit or pre-strains, okay, so we may have different sources of strain. So among these strains, okay, so we have many different strains, but the Hooke's law is applied to only the strain caused by the stress. Okay, the Hooke's law is applied only here. This is governed by the material law. So in this chapter, or in this class, my material law is what? The strain caused by stress is proportional to stress, then the proportional coefficient is 1 over elastic modulus. and then stress. Is it clear? And then here epsilon total, the strain, total strain is the strain what we can measure, okay? This is the strain what we can measure. That's why instead of using the total, so simply I want to call just epsilon. And then make sure that total strain, it is subjected to the compatibility condition. Subjected to the compatibility condition. Do you remember I emphasized you several times that when you check the compatibility between the displacements and strain, do not think about the sources of deformation. So we only check what we observe as the consequence of deformation. So which means we are interested in the total strain, okay? The total strain, not the individual strain components. Okay, let's say to simplify the problem, so we have only the thermal strain. So thermal strain, so let's consider thermal strain. Instead of having the thermal strain, let's drop all other things, okay? Then my total strain, okay, say my total strain is given by the strain caused by the stress plus strain caused by the temperature change. The strain caused by the temperature change comes from the high school physics class. The strain caused by temperature change is proportional to the temperature change. And then this can be given by the thermal expansion coefficient and then temperature change. Okay? And then here's alpha is called thermal expansion coefficients, or thermal dilatation coefficients. In 우리말, it is called 열팽창계수. Okay? Okay. Then how do you write material law? So my material law, the Hooke's law is given for only the stress and then the relative strain. So my Hooke's law is stress is elastic modulus times the strain caused by the stress. So from this equation, the strain associated with the stress is equal to the total strain minus the thermal strain. So if you have only the thermal strain as the non-mechanical strain, so let's plug in the mechanical strain here. Then this is elastic modulus the total strain minus thermal strain. It's very easy, right? And then if you expand this, then this is equal to elastic modulus and strain minus elastic modulus the strain, thermal strain, minus E alpha delta T. And this is called thermal stress. 열응력. Okay, let's consider an example. So if you consider an example, so I have a bar. Okay, and point A and point B. And then its temperature increases by delta T. Temperature increase here, delta T. Then make sure that I have one reaction, RA and then RB. because this is unknown. Okay, so although we do not have any external force, but we don't know how big or how small the reaction forces are yet. Okay, we don't know that, so we have to check the force equilibrium and other stuffs. Okay, look, so first we have to define the coordinate system x here, and then with respect to this coordinate system, so I can define the displacement field. Okay, so here look at this. At point A, ub is equal to 0. At point B, ub is also equal to 0. This is my displacement field. It's 0. Okay, 0. Then because my displacement field is equal to 0, and how about my strain field? My strain field is also 0. A and B. Okay, this is my strain field. Alright, now because I have a strain, then using this formula I can calculate the stress field. My stress is equal to elastic modulus, and then as you note here, my strain is equal to 0 in this member. 0 minus the thermal strain. The thermal strain is alpha delta T. Alpha delta T is equal to minus E alpha delta T. Is it clear, right? Okay. So the minus sign means my stress is compressive. So let's consider free body diagram. Let's consider free body diagram here. And then I have stress field, sigma. And then here my sigma is minus E alpha delta T. Oh, I don't know what happened today. Sorry about it. So RA, and then this is part of my member. And then we have positive stress field. This is sigma minus E alpha delta T. So let's check the force equilibrium. Then RA plus, and then it already has minus sign. So E alpha delta T is equal to 0. That's why my RA is equal to E alpha delta T. Is it clear, right? Let's check the other part. So if you check the other part, now I have part of the structure like this, and then we have RB, and then this is my stress sigma. The sigma is given here. Okay, so let's consider the force equilibrium. So minus, and the minus E alpha delta T. Oh, by the way, I need to multiply cross-section area. Sorry about it. A. And then the cross-section area plus RB is equal to 0. That's why we can determine the reaction very easily. This is equal to minus E alpha delta T times cross-section area. Is it clear? Any questions? Do you have any questions? Okay, so let's consider another application. 동현이. Yes, go ahead. 동현이, 이 elastic modulus is not limitless. 온도 변화로 적은 것은 스트레인에 영향을 주는 게 스트레스와 온도 변화. I don't understand your question clearly. The E means strain, right? The strain is equal to strain caused by the stress plus strain of temperature change. No, what I'm saying is you can how do I say, you can add up all the strains, okay, all the sources of strains to get the total magnitude of strain. This is comparability. So make sure that in force equilibrium side, what is in the force equilibrium side? Say we have force and then stress and displacement and the strain, okay? So in this diagram, so if you draw a line here, they don't, what I mean, the force stuff have nothing to do with displacement, okay? So unless you consider the stress and strain relation, the force stuff is governed by the nonlinearity found in stress axis. That's why, actual superposition of stress field, it is not that straightforward, especially if you have nonlinearity. But if you consider the strain here, so we have many different sources of strains. For example, the strain caused by the stress, the strain caused by the temperature change, the strain caused by the humidity change, the strain caused by any pre-stressing or pre-strain, whatever, or the misfit, the strain and misfit. So if you add up all the strains, that's gonna be the total strain. Blah blah blah, okay? But the strain subjected to the compatibility is only the total strain. Okay, this guy is subjected to the compatibility. So last time we considered compatibility for this strain, right? But now we want to generalize the argument. So if you want to check the strain compatibility, this strain is the total strain, okay? The total strain. The reason last time that I considered these many strains, but in our textbook, the textbook consider only the thermal strain. That's why I didn't write all these stuff, okay, to simplify the problem. But this is true. So you can superpose, you can add up, any the individual strains to obtain the total strain. So if you have any other sources of strain, yes, it's also fine, okay? But for example, let's consider another application. Let's say you have member, okay? You have member, and then let's say we have a temperature change and also the humidity change. And then the thermal strain is given by, thermal expansion coefficient alpha, and then the temperature change delta T. And then also the humidity strain. Humidity strain can be also given by, the humidity dilatation coefficient delta and the humidity change. So which means the total strain is equal to strain caused by stress, and then strain caused by the temperature change, and strain caused by the humidity change. And then this guy, the strain caused by stress is governed by the Hooke's law. So 1 over elastic modulus and stress. So make sure that both ends are fixed, which means the total strain should be equal to 0, isn't it right? That's subject to the compatibility condition. So 1 over elastic modulus of stress plus alpha delta T plus the humidity dilatation coefficient and the humidity change should be equal to 0. Then we can calculate the stress development very easily. You understand? 동현이, you understand? Let's consider another application. Let's say I have a simply supported one-dimensional member, and then I have temperature change. Okay, let's say how it works. Then in this case, if you introduce a coordinate system x, then this is my displacement field. Look at this. This is my displacement field. This is boundary condition. This is equal to 0. And then I may have one, non-zero displacement at this end. And this is my displacement field, isn't it right? Let's say this is the point A and point B, and that height is equal to UB. So can you calculate the strain here? Yes, we can calculate the strain. Strain is equal to UB divided by, say, initial length is L. This is a strain. Is it total or the strain caused by stress or the strain caused by temperature? So make sure that this is total strain. The total strain which is subjected to the displacement compatibility. Is it clear, right? And then we need to subtract to use the constitutive law. We need to calculate the mechanical strain. The mechanical strain is total strain minus any non-mechanical strain. Here non-mechanical strain is strain caused by the temperature change. This is equal to UB divided by the length L. This is the strain subjected to the compatibility condition. So minus alpha delta T. Okay? Then can you calculate the stress value? Stress is equal to elastic modulus times the mechanical strain. This is equal to L elastic modulus and UB minus elastic modulus alpha delta T. Isn't it? So now next step, we want to use the free body diagram to check the force equilibrium. This is my free body diagram. And this is my stress, right? Let's use this space. And this is my stress, and there is no external force here. There is no external force at point B. And then let's use the force equilibrium. Sum of force in that direction should be equal to 0. And then the cross-section area is given by A, the EA over L UB minus EA alpha delta T. These are forces, right? And there's no external force. That's why it should be equal to 0. So EA is cancelled. So which means I have displacement UB is equal to alpha delta T and then length L. Okay, and then the how big is the stress? Here the stress is equal to 0, so free expansion. Any other questions? Let's consider another application. So here so another application is called pre-stressing. In 우리말, it is called pre-stressing. There is no Korean counterpart. Okay, look. So here I want to consider cross section. So let's consider a rectangular cross section. Okay, but in the center of this rectangular cross section, I have a bar. And this bar is embedded. Okay, this bar is embedded as a part of the structure. So I have rigid plate here. And then let's say this is concrete. And then this is steel. Okay, so what we want to do is we want to do a very interesting job here. So here in the steel, in this steel, so we introduce the negative strain in advance. We want to introduce a negative strain in advance, epsilon p. So for instance, let's say the length of this member is equal to, for example, how to say 10 meters, 10,000 millimeters, but I prepared the length of steel. Length of the steel is, I prepared only, how they say, 9,900 millimeters only. So I have small length, okay, smaller length than the length required. But what's the length difference then? The length difference is, it should be originally 10,000 millimeters, but now I have only, sorry. Now I have only 9,900 millimeters, but originally it should be 10,000 millimeters. The difference is, so if I calculate the difference, the difference is 9.99 millimeters. A small difference, okay? Then let's try to calculate the strain. So the strain is minus of 0.99, and then the reference length is 10,000. This is equal to, then my strain is 0.00099. So I have very small strain, and this is called pre-strain, okay, the pre-strain. Alright, so now let's try to make sure that this pre-strain has nothing to do with stress, okay? Nothing to do with stress development. So this strain was caused by another way, okay? Another source. So here to analyze the structural system, so we need to introduce a coordinate like this, x, and I'm going to call A and B. So as usual, and this is my displacement, and x, and the point A and point B. And this is my displacement field. This is UB. Alright, then how do you calculate the strain? The strain is by using the comparability, we can calculate the strain. The total strain is UB divided by the length L. Isn't it right? So now let's try to calculate the stress of concrete. In the case of stress of concrete, is equal to sigma c is equal to elastic modulus times the strain of concrete. The strain of concrete is same as the total strain. This is equal to, elastic modulus of concrete, and then divide by the length L, the UB. And then how about the stress of steel? Stress of steel is elastic modulus of steel, and then here we have pre-strain, so non-mechanical strain, isn't it? So this is a total strain. Total strain is UBL minus, and then we need to count the pre-strain. Okay? Alright, so now let's check the free body diagram. Now let's check the free body diagram here. Then if you do that, then we have the stress-free end at point B, and then we have two different sources of forces here. This is sigma c times the stress of concrete times the cross-section area of concrete, and then stress of steel times the cross-section area of steel. So of course, sum of these two should be equal to 0. So from these two, ESAS UBL minus epsilon P plus EC UB over L should be equal to 0. And by the way, I need to multiply the cross-section area of AC. Okay? Okay, and then my UB, we can calculate UB by using this formula. 델타 L, 동현이 델타 L은 마이너스 100가 아닌가요? Where? 델타 L 마이너스 100. Hold on. 9900 minus 10. Yeah, minus 100. What's wrong here? Sorry. Minus 100. Sorry about it. And then 100 divided by 10,000. 0.01 minus 0.01. Sorry about it. Actually, sometimes I'm confused, when I handle real numbers. Usually I deal with variables instead of real numbers. I ask my TA to handle the real numbers. Sorry for this mistake. because I'm making mistakes in many different places. You have to check my lecture very carefully. Okay, here you can how you can calculate the displacement caused by the pre-strain. Actually, the pre-strain technology is widely used in civil engineering application. I wonder if you have ever heard about the pre-stressing concrete technology, PSC concrete. Because concrete is very weak in tension, that's why we don't like to shift the stress condition to the compression side instead of having the stress field. So we intentionally introduce the pre-strain into the steel, and then that steel used for the introduction of the pre-strain is called pre-stressing tendon. in 우리말 프리스트레싱 긴장제. 혹시 누가 아이패드 왜 그러는지 아는 사람 나 좀 알려다오. 오늘 왜 이러는지 정말 모르겠군. Okay, today I talked about and I reviewed how we approach statically indeterminate structures. The first approach was the procedure given in the textbook, so-called displacement compatibility method, the 변이적합법. The 변이적합법 is nothing but the principle of superposition for linear system. And then you can, using the principle of superposition, you can convert your statically indeterminate structure system into sum of many statically determinate structures. And then you solve individual structural systems by using the force equilibrium and then formula. You calculate the strain, displacement, or reactions. And then you superpose all the reactions, all the displacement to achieve the boundary condition. Then you can solve for the reaction, actual reactions. Okay? Or you can use the three conditions in another approach. You define first the displacement field, and then you calculate the strain, and then you calculate the stress, and then you calculate the internal forces, and then you compare the internal forces to satisfy the force equilibrium condition with the external forces. Okay? So you can choose any method to solve your problems. And then another approach, another subject that we discussed today is non-mechanical strain. Okay, non-mechanical strain. Here, the key point to understand the non-mechanical strain is Hooke's law is only for the strain caused by the stress and then stress value. Okay, so we can define the material behavior for the pair of stress and strain, especially strain caused by the stress. So, but the strain subjected to the compatibility condition is not the strain subjected to the material law. Okay? The strain subjected to the displacement compatibility condition is the total strain. So make sure that when you check the compatibility, we don't care about the stress or we don't care about the forces. Okay? So we check all the strains, the actual strains. We don't care about the fact that the strain was caused by the stress, the strain was caused by the thermal dilatation, the strain was caused by the humidity change. So we consider only the total strain. Only the strain caused by the stress is subjected to Hooke's law. That's the key point to understand this thermal effect chapter. Is it clear? Okay, we have bolt in this slides. We have bolts and turnbuckles. Using if you advance this nut in certain number of revolutions, so we can introduce some kind of pre-strain here. So if you advance this nut in this direction, so we may introduce, how they say, some negative pre-strain, isn't it? So, okay, because we fastened the bolt, so we may introduce negative pre-strain. Okay. And the next subject is how we measure the stress in inclined sections, because this is a little bit different subject from other subjects, and I'd like to discuss this subject next time. So next time we'll move to the torsion chapter after discussing the stress, how we read the stress on inclined sections. So before we finish today's lecture, if you have questions, so I'd like to discuss with you for that questions. Any questions? So if you don't have questions, let me start my lecture here today.